Hey guys, welcome. Yeah, so I hope everyone is well. And particle motion is an important topic in the application of derivatives. And it is taught both in Calculus 1 and Calculus 2, and therefore why the title at the top is what it is. Now, the position of a particle may be given as a vector, so therefore the velocity. And so if we're looking at the position as a vector, then the question would be a little bit different. What we have here is a position function that is given as a polynomial, but as you'll see in going through all of the parts of this question, I will have covered all of your bases for particle motion questions. All right, so let's commence. The first question is, what is the velocity at t equals 3 seconds? Again, the position of the particle is given by this polynomial, and position is usually denoted as s or x. And the velocity, we should know, is the derivative of position. So here, this first part is very easy. The velocity v of t of the particle is just going to be the derivative of the position, it's a poor s prime of t. And so if we take the derivative of this polynomial, forgive the color coding, I'm going to abandon it. Like, I'm not going to write a black constant and then the t's being red. I'm just going to go forward, right? And so what's the derivative of this? Well, it's going to be 3 times a third t squared. So that's just t squared. And so this polynomial is very well designed, as you'll see. And then it's going to be minus 6t, right? And then it's going to be plus 8. Cool. And so then for this first part, the velocity at time t equals 3 is just v of t, or s prime of t evaluated at 3. So s prime of t at 3 is going to say s prime of 3, and that is 3 squared minus 6 times 3, and then plus 8. And so what is that? That's 9 minus 18, that's minus 9, and then plus 8, I believe that's negative 1, right? Okay, cool. So the velocity at time t equals 3 is negative 1, and if you take the units into account, that's going to be meters per second, right? Velocity is measured in units per second, right? Okay, all right, cool. So that's that for this part. Next part. When is the particle at rest? Well, the particle is at rest when the velocity is equal to 0. That's s prime of t is equal to 0. So if we set v of t equal to 0, then that means that we have t squared minus 6t and then plus 8 equals 0. And this is a factorable quadratic, and that's why I said it's well designed. So it's t minus 4 times t minus 2 equals 0, from which we see that t is equal to 2, or t is equal to 4. So the particle is at rest at time t equals 2 seconds and at time t equals 4 seconds. Okay, and next we have to find the displacement of the particle in the first 5 seconds. But let's look at this together with finding the total distance traveled by the particle in the first 5 seconds. It's very, very important to distinguish between displacement and total distance. Notice that these are the 2 underlined items. In fact, they are the only 2 underlined items where I wanted to really highlight that they're very related and yet very different, okay? All right, so the displacement of the particle is easy picking. It's easy to answer. It's simply s of 5, where did it end up at 5 seconds, minus where it was to start, s of 0. So s of 5 minus s of 0. Notice if we were not given the position function, but rather the velocity function at the beginning, then this would be the integral from 0 to 5 of v of t dt, right? If, again, we did not know the position function and we knew the velocity function at the start. So this is displacement, right? Now, total distance, however, is a little bit more thinking and a little bit more work, and this is how exactly. So we'd answer total distance in this question in the first 5 seconds by writing the following. We'd have to do absolute value of s of 2 minus s of 0, and then plus s of 4 minus s of 2, and then plus s of 5 minus s of 4. I'll explain why. Of course, if we were given, again, the velocity function instead of the position function, then this here would look as follows. It'd be the integral from 0 to 2 of the absolute value of velocity. And so then this would be the integral from 2 to 4 of the absolute value of velocity, and yada yada. So why do we have to do this? Well, look at this. Look at the following. So suppose that the particle had moved in the following manner, which is actually an accurate depiction of the situation here, which is that it started, moving to the right, and then it stopped and turned around, started moving to the left, and then it started moving to the right again, so it turned around once more. Now, let's lay down this black line to represent the position of the particle. Then what's happened is this, right? So this black line represents the position. So the particle at time t equals 0 was right here at its starting position, and then it went at time t equals 2. It moved to the right all the way up to time t equals 2, so it moved forward. And then it stopped and turned around to move backwards. So this is t equals 4 in our specific situation. And finally, let's say t equals 5 is here, right? Allowing for time greater than 5, or as we saw in the number line analysis for velocity, that it was moving to the right beyond time t equals 4, right? Okay. Now, see, when you're doing displacement, all we care about is where was the particle at the start, which is right here, and then where did it end up at time t equals 5, which is right here. So for displacement, all we want to know is where was it at the start and where did it end up, and so we measure just this distance. However, for total distance, we need to measure not just times when it was moving to the right, but also times when it was moving to the left. Notice that since this black line is supposed to be the position of the particle, its position at time t equals 4 is to the left of its position at time t equals 2. So when you do s of 4 minus s of 2, this would be a negative number, but it's distance traveled, and distance traveled is positive, right? And therefore why the absolute values are required. And otherwise, you see why we have to break it up into 3 parts, because, well, we need to measure this plus this little bit, yeah? Okay, cool. All right. Now, to conclude, we have 2 more questions to do, and these are perhaps the most interesting questions to ask. Well, at least the latter of the 2 coming up is the most interesting, and perhaps the most involved also, other than like total distance. I'd say total distance and the particle speeding up or slowing down are the most involved questions you can ask about particle motion. So here's what we've got left. First, find the acceleration of the particle at time t equals 3, and then, of course, we conclude with the best item for last, and that is the particle speeding up or slowing down? The most interesting question to ask. This is easy picking. So velocity is the first derivative of position, and acceleration is the second derivative of position. So a of t, acceleration, is s double prime of t, and therefore it is the first derivative of velocity, v prime of t, because, well, v of t is the first derivative of position, and therefore the derivative of velocity has to be the second derivative of position, and therefore acceleration, right? Okay, now, if we recall we had written for velocity, let's start there, right? Why start all the way in the beginning? So velocity, we had said, was what? T squared, and then it was minus 6t, and then it was plus 8, and therefore the acceleration function here we see is a of t is equal to the derivative of velocity, and so that is 2t minus 6, right? It's 2t minus 6. And so then we plug in 3 into this, and we see that we're going to get a of 3 is equal to 2 times 3 minus 6, so that is 0. So the acceleration of the particle at time t equals 3 seconds is 0. All right. So, finalement, is the particle speeding up or slowing down? This is what you've got to do to answer a question like this. You need to draw 2 number lines, one for velocity and one for acceleration. So, let's do that and draw them exactly in the manner I'm drawing them. So first, the first number line is for velocity, and the second number line is for acceleration. Now, we'd already done the number line analysis for velocity, so our work is a little bit lighter. than it would have been otherwise had we not done that. Okay, so this is time t equals 0, so time t equals 0, right? And for velocity, we said that if this is t equals 2 and this is t equals 4, right, that the particle had positive velocity in these parts, that is, it was moving to the right, and then negative in these parts, and then positive again beyond 4, right? Okay, so now, coincidentally in this part, or is it a coincidence, we know that the acceleration is equal to 0 at t equals 3. Set this equal to 0, but we also found out by plugging in 3, right? And you're going to get t equals 3 is where the acceleration is 0. So then we should test a random number between 0 and 3 into the acceleration function to see if the acceleration is positive or negative in these parts. So if we like plug in 1, we're going to get negative, right? And so we see that the acceleration is negative in these parts, and then anticlimactically it's going to be positive in these parts, right? Like, so let's try t equals 4, and yes, surprise, surprise. So positive, positive, and on, right? Okay, so this is what you do next. To decide if the particle is speeding up or slowing down, what we do is we project the critical numbers from velocity onto the acceleration number line, and then we do the same for the critical numbers of acceleration, which is we project them the other direction onto the velocity number line. So that just means that we do this, right? We draw a vertical line right here at time t equals 2, and then a vertical line at time t equals 3. So notice the critical numbers both for velocity and acceleration need to be considered. And then the last one is t equals 4, right? And so then now we see that the number line is broken into 4 parts. Here, 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 here. Wherever velocity and acceleration have the same sign, the particle is speeding up. Wherever they have opposite signs, the particle is slowing down. So speeding up, in this case, would mean speeding up would be, well, where do they have the same sign? Between t equals 2 and t equals 3. So that's t equals 2 between t equals 2 and t equals 3. So 2 is less than, t is less than 3. So the particle is speeding up in these parts. And also, again, from t equals 4 on, because both velocity and acceleration are positive there. So let me write and, t greater than 4, right? Okay, cool. And the particle is slowing down elsewhere when velocity and acceleration don't have the same sign. So that's between 0 and 2, and where else? Between 3 and 4, right? Because they have opposite signs in there. Okay, cool. I won't bother writing that. I just said it, and that's good enough. I hope you enjoyed this. Keep watching, and yeah, take care.